Welcome back to Midnight Science. Tonight we drift far from the noise of the world and into the quiet places where stars are made and unmade. You will hear how light begins inside cold clouds of dust, how a sun lives its long, patient life, and how it lets go at the end. Nothing here will hurry you. If these slow journeys help you rest, a gentle like and a quiet subscribe lets others find this place too. Before we begin, soften your shoulders. Let your breath grow long. And if you feel like sharing, tell me in the comments where you are listening from tonight and what hour has found you here. Let us begin where every star begins, in the wide, quiet spaces between things. Look up on a clear night and the dark seems empty, a smooth black canvas with small bright pinpricks scattered across it. But that darkness is not empty at all. It is filled gently and almost invisibly with thin drifting clouds of hydrogen and dust. These clouds are so faint that starlight passes through them without much trouble. They are so cold that they hover only a few degrees above the lowest temperature the universe allows. And yet, inside these soft and patient regions, something miraculous is always happening. New suns are being born. We tend to imagine the universe as a place of speed and fire, of explosions and dramatic motion. The truth is closer to a slow and steady breathing. Most of what happens in the cosmos happens across millions or billions of years, in silences so deep that no instrument here on Earth can hear them. The birth of a star is one of those silences. It begins not with a flash of brilliance, but with a gathering, a slow drawing together of the thinnest material imaginable, a whisper of hydrogen settling into itself. If you could travel through one of these cold, drifting clouds, you would find that you could almost pass through it without noticing. The density of matter inside even the richest stellar nursery is far thinner than the best vacuum we can create in any laboratory on Earth. A single grain of dust might float for kilometers before meeting another. And yet, given enough time, given the patient pull of gravity, even something this thin can come together. Even something this quiet can become a sun. Astronomers call these gentle places molecular clouds. The name is technical, but the reality is closer to poetry. These are vast regions where hydrogen atoms have paired up into hydrogen molecules, where simple compounds like water and carbon monoxide have begun to form in the cold, where the temperature is so low that almost everything is still. They are the cathedrals where light first gathers. They are the dark rooms where the universe goes to think about its next bright idea. Some of these molecular clouds are small, only a few light years across. Others stretch for hundreds of light years, holding within them enough material to make hundreds of thousands of stars. The largest of them are called giant molecular clouds, and they are among the most massive single objects in any galaxy. If you could see one of them with eyes sensitive to the right kinds of light, you would see a vast and shadowed shape, full of folds and hollows, threaded through with quiet filaments where new stars are slowly assembling themselves. There is one such cloud closer to us than most. It hangs in the constellation Orion, a familiar shape in the winter sky of the northern hemisphere, visible as three bright stars in a line that form the Hunter's Belt. Just below that belt, in the place sometimes called Orion's Sword, there is a faint smudge of light. To the unaided eye, it looks like a single misty star, but that smudge is the Orion Nebula. It is one of the closest stellar nurseries to our world, about 1,300 light-years away, which sounds far until you remember that our galaxy stretches across 100,000 light-years and more. The Orion Nebula is a place where stars are being made right now, even as you listen to these words. Inside its glowing folds of gas, hundreds of young suns are taking their first slow breaths. Some of them are still wrapped in dust, hidden from our view, glowing only in the longer wavelengths of infrared light. Others have just emerged, blazing through their cocoons, lighting up the surrounding gas with the soft pink and green hues of energized hydrogen and oxygen. When you look at images of the Orion Nebula, you are looking at a moment in cosmic history that has not yet finished happening. The stars in that image are still being born. A little deeper into the universe, but no less tender, there is another nursery that has earned a quiet kind of fame. It lies within a larger region called the Eagle Nebula, about 7,000 light-years from Earth. Inside the Eagle, there rise three great columns of gas and dust, towering against the brighter glow behind them. Astronomers gave them a name that has stayed with us. They called them the Pillars of Creation. The pillars are not solid in the way that a stone pillar is solid. They are vast, slow rivers of cool, dense gas, slowly being eroded by the radiation of nearby young stars. Each pillar is several light-years tall. If you could shrink the speed of light down to the speed of a walking pace, it would take you years to stroll from the base of one of these pillars to its tip. And inside each pillar, hidden in the densest knots and folds, more stars are quietly forming. The pillars are nurseries within a nursery, slow sculptures being shaped by the same processes that gave birth to our own sun long ago. There is something deeply restful about knowing this, about knowing that even now, in the darkness above us, soft and unhurried processes are unfolding, that nothing in this work is rushed, that the universe takes its time. The force behind all of this gentle making is gravity. Gravity is often described in dramatic terms as something that holds planets in orbit, that crushes stars at the end of their lives, that bends the very shape of space. But before any of that, gravity is something quieter. It is the most patient force in the universe. It does not push or pull suddenly. It simply asks, over and over again, in the softest possible voice, for things to come closer to each other. And given enough time, things do. Inside a molecular cloud, every atom feels the pull of every other atom. Each of these pulls is unimaginably small, weaker than almost anything we could measure. But when you add up the gentle calls of trillions upon trillions of atoms across many light years, the sum becomes powerful enough to slowly reshape the cloud. Tiny, denser patches begin to draw in more material. Those patches grow heavier, and so they pull harder. They become a little denser still, and the pull grows again. This process can take 1,000,000 years, 10 million years, sometimes longer. It is gravity speaking very slowly to itself. Something else helps along the way. Molecular clouds are not perfectly still. They are stirred by passing supernovae from earlier generations of stars, by the slow rotation of the galaxy, by the pressure of light from nearby suns. These small disturbances act like a hand passing softly over a pond, sending ripples through the cloud. Where two ripples meet, the gas grows a little denser. Where the density crosses a quiet threshold, gravity takes hold more firmly. The cloud begins to fragment, not violently, but the way a slow piece of music breaks into separate notes. Each fragment will eventually become a separate star, or a small system of stars. You can imagine a stellar nursery as a vast and dim hall, in which, here and there, soft pools of warmth are slowly forming. Each pool is a future sun. None of them know yet that they will one day shine. They are simply gathering, growing heavier, growing closer to themselves. The cloud around them is dark and cold, full of the silence that has waited for them for millions of years. As one of these fragments collapses, something quietly remarkable happens at its center. The gas falling inward begins to compress. As it compresses, it warms. This is one of the oldest and simplest rules of nature. Squeeze something, and it grows hotter. Slowly, at the heart of the collapsing fragment, a small, warm region begins to form. It is not yet a star. It has not yet found the trick that makes stars shine. But it is the first ember. It is the first hint of what is to come. Astronomers call this the protostar phase. The word means first star, the earliest version of what a star will become. A protostar is wrapped in its own dust, still feeding from the cloud that surrounds it. Material continues to fall inward. spiraling down through a flattened disk of gas that swirls slowly around the new ember. This disk is important. From its quiet rotation, planets may one day be born. Our own sun once had such a disk, and from it came the Earth, the Moon, the wide oceans, and you. The protostar grows for hundreds of thousands of years, sometimes for 1,000,000 or more, in this gentle veiled state. It cannot yet be seen in ordinary light, because the dust around it is too thick. But it glows in the warmer, longer wavelengths, like a faint heat in the dark. Inside the dust, its core grows hotter and denser. The pressure climbs, the temperature climbs, and still it is not yet a star. There is a quiet patience here that is hard to describe. Imagine a candle taking 1,000,000 years to begin burning. Imagine holding your breath across the lifetime of mountains. The slow collapse of a stellar nursery is like a breath held across eons, drawn in by gravity, waiting for the moment when the universe will finally let it out as light. The smaller, gentler stars sometimes pass through a particular phase in their youth, a phase that has its own soft name. They are called T Tauri stars, after a young star in the constellation Taurus, where this kind of behavior was first noticed. T Tauri stars are restless young suns. They have not yet settled into the steady rhythm of adulthood. Their surfaces are turbulent. They flare and dim irregularly. They are still surrounded by the leftover disks of dust from which planets are slowly assembling. They are still drawing material in from those disks, growing heavier and more luminous by small, uneven amounts. A T Tauri star is a sun still finding its rhythm. It is a child of the cloud, no longer fully hidden, but not yet fully born. Its light, when we can see it, is a warm orange, sometimes flickering, sometimes quiet. Around it, planets are coalescing from dust grains the size of smoke particles. Around it, the disk is slowly thinning, as some of the material falls into the star and some is swept away by gentle stellar winds. In a few million years, the T Tauri star will calm. Its flares will fade. Its disk will dissipate or settle into stable orbits. It will become a steady main sequence star, much like our own Sunday. Our sun was once a Te Tauri star, 4.5 billion years ago. It was restless then. Its young face flickered. Around it, the dust began to gather into clumps. Those clumps became pebbles, then boulders, then small worlds, then the planets we know. Earth itself was forged in the soft, restless light of the young Sunday. The water in your blood, the air in your lungs, the calcium in your bones, all of it was once swirling in a disk around a young star not unlike Te Tauri itself. The connection is gentle, but it is real. You are made of the leftover dust from a stellar nursery. Imagine this scene. Picture the sun as a young restless star, glowing in a cocoon of dust. Picture the disk around it, broad and faintly shining, full of slow grains and quiet flows. Picture the first planetesimals forming, small bodies the size of mountains tumbling slowly through the disk. Picture them growing, gathering one another, sweeping up the dust around them. Picture the Earth, still molten, still gathering its first oceans from icy comets that fell from the outer regions of the disk. All of it lit by the soft, uneven light of a sun that had not yet decided to be calm. That is the kind of moment happening in countless other nurseries right now, across the galaxy, in clouds, like Orion and like the Eagle, in nurseries we have not yet mapped. Restless young stars are turning their slow dust into new worlds. Each one is a future neighborhood for whatever might come to live there. Each one is a soft beginning. But there is still one more step before a star can be called a star. A protostar, even a restless T Tauri star, is shining mostly because it is contracting. Its light comes from the conversion of gravitational energy into heat. This is borrowed light. It cannot last forever. Eventually, if nothing else happens, the protostar would simply cool and fade. Many small bodies in our universe do exactly this. They contract, glow faintly for a time, and then settle into the long cold of brown dwarfs, the failed stars, which we will speak of another night. But if the gathering body is large enough, if it has drawn in enough hydrogen, something else happens at its core. The temperature climbs past a soft and ancient threshold. The pressure crosses a quiet line. And there, deep inside the new ember, the hydrogen begins to do something it has never done before in this place. It begins to fuse. Fusion is the word for it, but the word does not quite capture how gentle it is at the beginning. Two hydrogen nuclei, normally repelling one another, come close enough that a deeper force takes over. They merge. In merging, they release a tiny amount of energy, a small, soft glow of light born from the joining of matter. Multiply this small, soft glow by the unimaginable number of hydrogen atoms in a star's core, and you have the slow, steady fire that lights a sun for billions of years. The first moment of true fusion is not an explosion. It is a quiet ignition. Imagine a single match being struck in a vast, dark hall. Imagine the flame catching, growing slowly, becoming steady. The new star wakes. The cocoon of dust around it begins to be pushed back, gently at first, by the new pressure of light streaming outward from the core. The star is not yet visible from far away. The dust still wraps it. But inside that dust, a sun has begun to shine. It can take many more years for the star to fully emerge from its nursery. The dust slowly thins. The leftover gas is gently blown away by the young star's growing radiation. The disk around it becomes quieter, more orderly. Planets, if they are forming, begin to settle into their orbits. And finally, after all this patience, after all this waiting, the cloud parts and a new star stands revealed in the dark. There is a particular kind of beauty in this moment. After 1,000,000 years of slow gathering, after the long, unhurried work of gravity, after the restless flickering of the protostar and the gentle calming of the T-Tauri phase, the new sun simply begins to shine. Not loudly, not with announcement, just steadily, the way a quiet candle settles into its flame after the first flicker. The universe has made another star. Somewhere right now this is happening. In a nursery you will never visit, behind a curtain of dust you will never part, a sun is taking its first long calm breath. Its light has not yet reached us, and may not for thousands of years, but it is shining. It is shining patiently into the same dark from which it came, in a galaxy that has been making and remaking suns for more than 13 billion years. This is the slow miracle that we tend to forget when we look up at the night sky. Every star we see was once a soft patch of cold gas inside a molecular cloud. Every star spent a long invisible childhood, gathering itself, warming, deciding what kind of light it would become. Every star, no matter how bright, was once a quiet ember inside a vast and patient nursery. And the same is true of the sun that warmed your skin today, that drew the colors out of the morning sky, that lit the rooms where you read and ate and rested. Your sun, too, was once unborn. Your sun, too, was once a slow gathering inside a cloud now long since drifted apart, its dust scattered across this small corner of the galaxy. You live by the light of a star that was once a question the universe was asking itself. Let that thought settle in you for a moment. There is no urgency to it. Nothing in this work was ever rushed. The cloud waited. The gravity waited. The dust waited. The protostar waited. The T-Tauri star flickered and waited, and in time the slow, soft answer came. A new star, a new sun, a new chance for light to be in a place where there had been only quiet. This is how all stars begin, in darkness, in cold, in patience, in the gentle insistence of gravity asking, again and again, for things to come a little closer. And then, in the smallest possible moment, an exhale, an ignition, a new light in the dark. Rest with that image. Hold it lightly, the way you would hold a sleeping bird in your hands. The universe is full of these soft beginnings. It is full of cathedrals of gas where new suns gather in the dark. It is full of nurseries, where the slow, patient work of light is happening even now, even as you breathe, even as your body grows heavier into the bed beneath you, even as the room around you settles into its own quiet night. And from these soft beginnings come the long, calm middles, the patient adult lives of stars, where most of the light in the universe is made. We will move into those long, patient lives next, where suns like our own settle into their steady fire and burn for billions of years. But first, breathe in, breathe out. Let the nurseries of light stay with you for a moment. Let the dark feel a little gentler. The universe has been making stars for a very long time, and it is making them still. Once a star has been born, once the first quiet ignition has caught at its core, something remarkable settles over it. A balance, a steady, soft equilibrium that can last for billions of years. The dramatic part of stellar life, the gathering and the ignition, is over almost as soon as it begins. What follows is the long middle, the calm, patient chapter where most of a star's existence unfolds. Astronomers call this the main sequence, but you might also call it the long, quiet breath of a sun. To understand the main sequence, picture two great forces holding hands at the center of every star. One of them is gravity, the same patient force that gathered the cloud in the first place. Gravity does not stop working once a star is born. It keeps pulling. It keeps asking every part of the star to fall inward. If gravity were alone, the star would simply collapse, crushed by the weight of its own immense body. But gravity is not alone. At the core, fusion is now happening, and fusion pushes outward. Fusion creates heat. Heat creates pressure. Pressure pushes back against gravity. And so a star spends its long life in this gentle tension, gravity pulling inward, fusion pushing outward, the two of them in such perfect balance that the star neither grows nor shrinks for billions of years. The whole vast structure of a sun, the immense burning sphere, is held together by this quiet conversation between two old forces. It is one of the most peaceful arrangements in the universe. You can think of it as a breath that does not end. A star inhales gravity, a star exhales light. The two motions cancel each other out, and the star is still. Not motionless, but still in the way a calm pond is still, even though deep currents move through it. This is the steady state of stellar life. This is where suns spend almost all of their time. Our own sun has been in this calm middle for about 4.5 billion years. That number is so large that it slips through the mind without being felt. So let us slow it down. 4.5 billion years ago, there were no people, there were no animals, there were no plants. There were not yet any continents in their current shapes. There were not even any oceans. The earth itself was just beginning to gather from the dust around the young Sunday, and the sun was already shining. The sun was already burning steadily, already settled into its long, calm life, already keeping its quiet promise to give light. It has been doing that ever since. Through all the long ages of geology, through the formation of oceans and the first appearance of single-celled life, through the rise of forests and the slow opening of flowers, through the brief flicker of human history, all of which has happened in the last sliver of the sun's lifespan. The sun has been steady through every one of these chapters. It has not grown noticeably brighter or dimmer in any way you would feel in a single human life. It has simply burned calmly, patiently, like a companion who has been there the whole time without ever needing to be thanked. There is something deeply comforting about this. The sun is the most familiar object in the sky, and yet it is also a star, one of billions and billions of stars. It is both small and ordinary in the cosmic sense, and it is also the single most important light in your life. Everything green that grows on Earth grows because the sun gives it the energy to do so. Every breath of oxygen you take exists because plants long ago learned to drink sunlight and turn it into air. The sun is not just out there. The sun is in you, in every motion of your body, in every warmth that moves through your skin. To understand how the sun keeps shining, we have to look gently at the work happening in its core. Deep inside the sun, far beneath its visible surface, the temperature reaches around 15 million degrees. The pressure is more crushing than anything we can imagine on Earth. Under such conditions, the hydrogen at the core is no longer simple gas. It is plasma, a state of matter where the electrons have been stripped away and only bare nuclei remain, swimming in a sea of free particles. In this hot, dense soup, hydrogen nuclei sometimes wander close enough to one another that the strange rules of the very small allow them to fuse. This process unfolds in a sequence that astronomers call the proton-proton chain. The name sounds technical, but the process itself is almost gentle in its slowness. It begins when two hydrogen nuclei, each a single proton, come close enough to merge. This is hard because protons carry the same kind of electric charge, and like charges repel. They have to be moving fast enough, and the temperature has to be high enough that they can briefly overcome that repulsion. Even then, the merging only happens because of a soft quantum rule that allows particles to do things that classical physics would forbid. When the two protons do merge, one of them transforms into a neutron, and a small particle slips away into the rest of the star. What is left behind is a nucleus made of one proton and one neutron, the simplest form of heavy hydrogen. That heavy hydrogen then meets another single proton and fuses again, forming a light form of helium. Two of those light helium nuclei then meet each other and merge, releasing two protons back into the soup and leaving behind a stable nucleus of ordinary helium with two protons and two neutrons. The whole sequence, from start to finish, has turned four hydrogen nuclei into one helium nucleus, and in doing so, it has released a tiny amount of energy, a small, soft glow of light born from the joining of matter. This is the slow conversion that lights our world. Hydrogen, the simplest and oldest element in the universe, is being patiently rearranged into helium inside the sun, and a fraction of its mass is being released as light and warmth. The sun is not burning in the way a fire burns. It is not consuming oxygen. It is, in a much deeper sense, turning a small portion of itself into light. Every second, the sun converts about 4 million tons of its own matter into pure energy. That is an astonishing number, and yet the sun is so vast that it can do this for billions of years without noticeably shrinking. There is a poetry hidden inside this fact. The sun is, very slowly, becoming light. Each day, a small piece of the sun travels outward as sunlight, falls onto the earth, warms the seas, feeds the plants, and finds its way eventually into every living thing. Each leaf, each blade of grass, each warm hand and beating heart is, in a quiet sense, a small piece of the sun that has changed form. The sun is not only above you, the sun is also inside you, transformed into bodies and breath. But the journey of that light, before it ever reaches the leaves and your skin, is itself one of the strangest and most beautiful stories in the universe. Light is fast. In empty space, light travels at 300,000 kilometers every second. A photon born at the surface of the sun reaches the Earth in just over 8 minutes. But a photon born in the sun's core deep inside has a much longer trip ahead of it. The inside of the sun is not empty space. It is densely packed plasma, layer upon layer of nuclei and free electrons. A photon born in the core does not travel in a straight line outward. It moves a tiny distance, perhaps less than a centimeter, before bumping into a particle. It is absorbed, then released again, in a slightly different direction. It moves another small distance, bumps again, is absorbed and re-emitted, over and over and over. This stumbling random walk takes time, an astonishing amount of time. By careful calculations, astronomers estimate that a single photon born in the sun's core takes on the order of 100,000 years to reach the surface. Some estimates are shorter, some longer, but all of them are measured in tens of thousands of years at the very least. The light that left the surface of the sun this morning, the light that warmed your face, was born in the core long before any human civilization existed, before the pyramids, before agriculture, before the last ice age receded. Think of that gently. The sunlight that fell across your hands today began its life inside the sun while mammoths still walked. By the time that photon reached the surface, it was already older than every human story. Then it leapt across the empty distance from the sun to the earth in just over 8 minutes, and arrived at the moment you happened to step into the morning. Sunlight is older than memory. Sunlight is a gift from a star that began wrapping it for you while the earth was still wearing the last of its glaciers. When the light finally does reach the surface of the sun, it leaves through a region that is itself in slow motion. The visible surface, called the photosphere, is not a smooth shining ball as it appears from far away. Looked at closely, it is covered in countless small bright cells, each surrounded by darker borders. These are the granules. Each granule is a vast column of rising hot plasma, perhaps the size of a small country, that pushes upward from below, spreads out at the top, cools slightly, and sinks back down at the dark edges. The surface of the sun is constantly boiling in this gentle way, like the surface of a pot of porridge that has been simmering for billions of years. Each granule lasts only a few minutes before it dissolves, and another rises in its place. If you could stand and watch the surface in real time, with the right kind of vision, you would see a slow, living mosaic, bright shifting tiles, all of them in motion, the whole face of the sun breathing in tiny patterns of rise and fall. It is a calm activity, even though the temperatures involved would be unimaginable to a human body. It is the sun simply being itself, simply moving its own heat from the depths to the open sky. Here and there on that bright surface, darker patches appear. These are the sunspots. To the eye, sunspots look almost like blemishes on the sun, small dark stains against the glowing face. But they are not flaws. They are places where the sun's magnetic field has grown so strong locally that it slows down the flow of hot plasma from below. With less hot material rising into them, those regions cool slightly, and so they look darker than the rest of the surface. A sunspot is still incredibly bright, hotter than almost anything we can imagine on Earth. It only appears dark because the surrounding photosphere is even brighter. Sunspots come and go in a slow rhythm. They are tied to the sun's magnetic activity, which itself rises and falls in a long cycle. Roughly every 11 years, the sun moves through one breath of activity. At the peak of the cycle, sunspots are numerous. Solar flares are more frequent. The sun's outer atmosphere is more energetic, and the curtains of light we call auroras are seen more often in the skies near Earth's poles. At the quieter end of the cycle, the sun's face becomes smoother, the sunspots fade, and the great star seems to settle for a few years before its next slow turning. 11 years. To us, that is a long stretch of life. A child can be born and become old enough to remember the world by the time the sun completes one of these breaths. And yet, in the sun's own lifetime, an 11-year cycle is a small twitch, a tiny rhythm. The sun has lived through hundreds of millions of such cycles already, and will live through hundreds of millions more before its long main sequence finally comes to an end. That is the most astonishing piece of all. The sun, which seems so vast and timeless to us, is itself only in its middle years. It has been shining for about 4.5 billion years, and it has roughly that much again to go in this calm, steady state before any major changes begin. The sun is, by the standards of its own life, neither young nor old. It is a mature star in the long, patient prime of its existence, doing exactly what it has done for ages, and exactly what it will continue doing for ages more. But not all stars live like this. The main sequence is a broad and varied family. Our sun is only one kind of member, one quiet type within a wider range. To feel the variety, we have to widen the lens. Many of the stars in our galaxy are smaller and cooler than the Sunday. They are the red dwarfs, and they outnumber every other type of star by a wide margin. A red dwarf is a small star, perhaps 1/10 the mass of the Sun, with a surface that glows in a deep amber light. They are faint. Even the nearest red dwarf to us, Proxima Centauri, is too dim to see with the unaided eye, despite being one of the closest stars in the sky. What red dwarfs lack in brightness, they make up for in time. Because they are small, they burn their fuel very slowly. Their cores are cooler than the Sun's, and their fusion runs at a gentler pace. A red dwarf can stay in its long main sequence not for billions of years, but for trillions. Some calculations suggest that the longest-lived red dwarfs will continue to shine softly for hundreds of times the current age of the universe. Think about that for a moment. The universe itself is about 13.5 billion years old. The longest-lived red dwarfs are estimated to live for 10 trillion years or more. Most of their lives have not yet begun. They are still, in the deepest sense, only at the start of their own slow stories. When our sun finishes its main sequence and changes, when most of the stars we see in the night sky have come and gone, the red dwarfs will still be quietly burning. They will outlive almost everything. They will be the last patient lamps in a much older universe, glowing into a slow, long darkness. At the other end of the family, the picture is reversed. Some main sequence stars are far more massive than the Sunday, 10 times its mass, 20 times, sometimes more. These are the blue and white giants, stars whose surfaces are so hot that their light shifts from yellow into white, and then into a brilliant blue. Their cores burn through hydrogen at a much faster rate. Their fusion is fierce. Their light is extraordinary. But this brilliance comes at a cost. A blue giant cannot stay on the main sequence for billions of years. Its fuel, no matter how abundant, is consumed too quickly. The largest of these stars may live for only a few million years before the calm equilibrium breaks down. By human standards, a few million years is unimaginably long. By stellar standards, it is the briefest possible life. A blue giant is a sun who blazes through its main sequence in what is, for the universe, the blink of an eye. So there is a quiet kind of justice in the way stars live. The brightest live the shortest lives. The dimmest live the longest. The sun, sitting comfortably in the middle, lives for billions of years and shines with a steady, moderate light. Time itself bends around different kinds of stars. A red dwarf has trillions of years to live without changing. A blue giant has less time than a single mammalian species. Our sun has billions, and we live our small, bright lives in the middle of one of its calm, quiet phases. When you look up at the night sky, you are seeing this whole family at once. Some of the points of light are red dwarfs, small and patient, with lifetimes longer than the universe. Some are stars like the sun, calm and steady. Some are blue giants, blazing for their brief moment, already nearing the end of their main sequence. Each one is living through its own pace of time. Each one is on its own journey. The night sky is a great gathering of suns, all in different chapters, all glowing quietly from across the dark. And yet, beneath all this variety, the same simple story holds. Every main sequence star is doing what our Sun is doing. Every one of them is balancing gravity and fusion, inhale and exhale, inward and outward. Every one of them is slowly converting hydrogen into helium, slowly turning a small portion of itself into light. Every one of them is, even in its calmest years, moving toward a future in which the balance will eventually shift. For the main sequence is not forever. Even for the longest-lived red dwarf, even for the most patient star in the deepest corner of the galaxy, there comes a time when the hydrogen at the core begins to run low. The fuel begins to thin. The balance between gravity and fusion begins to wobble. The star begins to change. Slowly, gently, sometimes over millions of years, always inevitably. This is true for the Sun too. As steady as it is now, as familiar as it feels, our Sun is also on a journey. Its calm equilibrium is not eternal. In about 5 billion years, its core will have used up most of the hydrogen there, and it will begin to transform into something new. We will follow that long, slow unraveling in another part of our night together. For now, simply rest with the Sun as it is. Rest with the idea that a great patient star has been keeping watch over the Earth for 4.5 billion years, and will keep watch for billions more. Rest with the idea that countless other suns are doing the same across the galaxy, each in its own time, each in its own kind of light. Rest with the idea that even the longest stellar lives are themselves only chapters in a larger story, and even the briefest blue giant was, for its time, exactly the sort of slow miracle the universe seems endlessly willing to make. The sun rose this morning. The sun will rise again. And somewhere in its great burning core, a photon born tens of thousands of years ago is still slowly making its way to the surface, where it will leap across space and find its way, perhaps, to a window near you on some quiet morning yet to come. Sleep gently with that thought. The light is on its way. The star is still calm. The long, patient lives of suns are still unfolding, all around us, all the time. When you look up at the night sky, the stars all seem to share the same kind of light, small white points against a wide black field. To the unaided eye, they appear almost interchangeable. A scattered field of similar lamps, all of them quiet, all of them distant. But this gentle uniformity is a kindness of distance. Up close, every star is its own being. Every star has its own size, its own color, its own temperament, its own way of living and dying. The night sky is not a uniform field at all. It is a quiet garden, full of different kinds of light, planted across many billions of years. Tonight, we will walk slowly through that garden. We will not try to meet every kind of star. We will simply pause beside the most interesting ones, listen to what they are doing, and move on. There is no hurry. The stars have been here for a long time. They will still be here when we are finished. Let us begin with the smallest, with the patient ones. The red dwarfs are the most numerous stars in our galaxy. For every sun like ours, there are perhaps 2 or 3 red dwarfs. For every blazing blue giant, there are thousands of these small, soft embers. They make up roughly 3/4 of all the stars in the Milky Way, and yet almost none of them can be seen with the unaided eye. They are too faint, too quiet, too tucked into the dark. You can walk under a clear night sky and not see a single one of them, even though they vastly outnumber every star you can see. A red dwarf is a small star, smaller than our sun, often less than half its mass, sometimes as little as 1/10. Its core is cooler, its fusion is gentler. Its surface glows in a deep amber light, sometimes leaning toward orange, sometimes settling into a soft reddish hue. If you could stand on a planet circling one of these stars, the day would feel like a long, calm sunset. The sky would not blaze, it would simply glow. Because red dwarfs burn so slowly, They live for unimaginable lengths of time. The smallest of them are expected to remain in their long main sequence for 10 trillion years or more. The current age of the universe, the time since the very first stars began to shine, is about 13.5 billion years. 10 trillion years is more than 700 times that. The longest-lived red dwarfs have not yet finished their childhoods. They have not yet reached their own middles. They are still, in the deepest sense, only at the start of their long stories. Imagine that. There are stars shining quietly in the sky tonight, whose lives have barely begun. When our sun finishes its main sequence and changes, when the brighter stars of the sky have come and gone, when whole generations of stellar life have passed, the red dwarfs will still be there. They will be the last calm lamps in a universe grown older and quieter. They will glow into the long darkness, soft and steady, until at last even they begin to fade. The closest star to our own sun is one of these patient embers. Its name is Proxima Centauri. It hangs in the southern sky, about 4.25 light years away, which means that the light we see from it left its surface around 4 years ago. Around Proxima, astronomers have found at least one rocky planet inside the gentle zone where liquid water might exist. We do not know if anything lives there. We may never know. But the idea is a soft one to hold. A small amber sun, a small rocky world, both of them shining and turning quietly, the closest neighbors the Earth has in the entire galaxy. From the red dwarfs we move toward warmer light. We come now to the stars like our own. Yellow stars are not as numerous as red dwarfs, but they are still common throughout the galaxy. Our sun is one of them. Astronomers place it in a category they label by letter, but you do not need the letter. You only need to know that the sun belongs to a wide family of similar suns, each of them medium in size, each of them stable, each of them shining with the warm yellow-white light that we know so well. From a distance, the sun would look much like many other stars in this group. It is not the brightest among them, nor the dimmest. It is comfortably in the middle. These yellow stars are quiet workhorses of the cosmos. They burn calmly for billions of years. They are stable enough to allow planets to settle into long orbits. They are gentle enough to allow oceans to form and to remain. Whenever astronomers search for places that might be hospitable to life, they tend to look first at yellow stars and their close cousins because of the long, calm time they offer. Time is the great gift of these suns. Time enough for slow processes to unfold. Time enough for chemistry to find its way into biology, if it ever will. Our sun is one such gift of time. It has given the Earth more than 4 billion years of steady warmth, and it has billions more to give. That length is the canvas on which all life has been painted. Every leaf, every wing, every patient, slow change in the long story of evolution has happened in the steady sunlight of a single quiet star. But not every star is so patient. Beyond the yellow suns, the family grows brighter and hotter and more brief. White stars are larger and warmer than the Sunday. Their surfaces glow at temperatures high enough that the yellow shifts toward pure white. They burn through their hydrogen more quickly and live for shorter times. Where a yellow sun like ours might live for 10 billion years on the main sequence, a typical white star might live for only 1 billion or 2. That is still a long time by any human measure. But it is a fraction of what the sun has, and a smaller fraction still of what a red dwarf has. Beyond the white stars come the blue ones. These are the great burners of the galaxy. Massive, fierce, brilliant. A blue star can be many times the mass of the sun, with a surface so hot that its light is shifted into the blue and violet end of the spectrum. They blaze with a brightness that is almost difficult to imagine. A single blue giant can shine with the light of 100,000 suns or more, lighting up the gas around it for many light years in every direction. But blue giants pay for their brilliance with their lives. Their cores burn through hydrogen at a tremendous rate. They cannot keep that pace up for long. The very largest blue stars live for only a few million years before the calm balance at their cores begins to fail and they begin their journeys toward dramatic endings. A few million years sounds long, and by the standards of our lives it is, but by the standards of the universe, it is the shortest possible kind of star life. A blue giant is a sun who burns bright and goes quickly, leaving the gas around it lit and slightly enriched for the next generation of stars to use. You can see some of these brilliant giants in the night sky. The stars of the constellation Orion, for example, are mostly hot, bright suns of this kind. Rigel, the bright blue-white star at one corner of Orion, is a blue supergiant, far larger and far brighter than the Sunday. The light of Rigel that reaches your eyes left its surface around 860 years ago. Through every century since, that light has been traveling through space, slowly making its way to you. By the time it arrives, you are simply looking up and seeing a single bright point. You may not feel its history, but it is there, in every photon. Now, leave the single stars behind for a moment, and come with me into a different kind of arrangement. For many stars do not live alone. When astronomers look closely at the suns of the galaxy, they find that a great many of them are paired. Not single quiet lamps, but two stars orbiting a shared center of gravity, dancing slowly around each other across the long ages. These are the binary stars. Sometimes they are close together, almost touching, exchanging streams of gas across the small space between them. Sometimes they are far apart, drifting in slow, wide orbits that take thousands of years to complete. But always they are bound. Always they are in conversation. Beyond binaries, there are triple star systems, quadruple systems, even more complex arrangements. The bright star Castor in the constellation Gemini, for example, is actually a system of 6 stars, 3 pairs of close binaries, all moving together in a more distant slow dance. From far away, Castor looks like a single bright star. Up close, it is a family of suns, gathered together by gravity, each pair turning around each other, while all 3 pairs turn around a shared common center. There is something gentle in this. The image of stars in pairs, of suns who never have to be alone, of slow dances that have been going on for billions of years. Some binary stars are so closely bound that they will spend their entire lives together, growing old at the same pace, shaping each other through their gravity. Others may have begun their lives together in the same nursery and stayed paired ever since, like siblings who never quite drifted apart. The galaxy is full of these soft companionships. More than half of all stars, by current estimates, live in some kind of multiple system. Our sun is one of the lonelier ones. It travels alone through the dark, with only its planets for company. If you could fly slowly through the galaxy and observe its stars, you would see this everywhere. 2 suns rising together over an unseen world. 3 suns wheeling slowly across an alien sky. Whole small families of stars holding each other in long, quiet patience. Some of those worlds may even harbor life that has never known the strange experience of having only one sun in the sky. We move on now to a different kind of unusual light. To stars who do not shine steadily, but who breathe. A variable star is a star whose brightness changes over time, in a pattern that can be measured. Sometimes the change is small, sometimes it is large. Sometimes the rhythm is so regular that you could set a clock by it. Sometimes it is irregular, almost moody, brightening and dimming in ways that astronomers are still trying to fully understand. Among the most famous variable stars are the Cepheids. They are large, bright stars that pulse with a steady rhythm. Each pulse is a slow physical expansion and contraction of the star itself, a kind of breathing across days or weeks. As the star swells slightly, it cools and dims. As it contracts again, it warms and brightens. The pattern repeats, with a regularity so reliable that astronomers in the early 20th century were able to read it like a kind of celestial clock. A young astronomer named Henrietta Swan Leavitt, working in the early 1900s, noticed something quietly miraculous about Cepheid variables. The longer their cycle of pulsation, the brighter the star actually was. A Cepheid that took 10 days to complete one pulse was inherently brighter than one that took only 3 days. Because of this relationship, anyone who could measure the time of a Cepheid's pulse could know how bright that star truly was, no matter how far away it sat in the sky. This was an extraordinary gift. It meant that Cepheids could be used as distance markers across the cosmos. By comparing how bright a Cepheid truly was to how bright it appeared from Earth, astronomers could calculate how far away it must be. And once they could do that, they could begin to measure the actual size of our galaxy. They could measure the distances to other galaxies. They could begin, for the first time, to grasp the true scale of the universe. Much of our sense of how large the cosmos truly is comes from those slow, steady pulses. Cepheid variables were, and still are, soft lighthouses scattered across the dark, each one quietly telling us how far it lies from our small world. Whenever you hear a number about the distance to a faraway galaxy, somewhere behind that number is a Cepheid, pulsing patiently, helping us know our place in a much larger room. Now, let us walk to a corner of the garden where the strangest residents live. Not the most famous, not the brightest in our sky, but the largest, the hypergiants. Some stars grow to truly extraordinary sizes. Not just giant, not just supergiant, but the next category beyond, where the word hypergiant feels almost too small for them. These are stars whose outer layers have swollen to sizes that the human imagination has difficulty holding. There is a star in the constellation Scutum called Uy Scuti. It is one of the largest known stars in our galaxy by radius. If you could replace our Sun with Uy Scuti, its outer surface would extend far beyond the orbit of Earth, far beyond the orbit of Mars, swallowing the inner solar system entirely. The orbit of Jupiter itself might lie inside it. It is so vast that light, traveling at 300,000 kilometers per second, would take many hours to journey from one side of it to the other. There is another, even more astonishing in some measurements, called Stephenson 2-18, in a distant stellar cluster. Some studies suggest it is even larger than Uy Scuti, although these measurements are uncertain because such stars are so far away and so unstable that pinning down their exact size is genuinely difficult. Whether or not it is the absolute largest, Stephenson 2-18 belongs to a small, quiet club of stars who push the very limits of what is possible. These hypergiants are not stable in the way our Sun is stable. They shed material into space at huge rates. Their outer layers are loose and slow, almost transparent at the edges. They glow in the deep red part of the spectrum because their outer surfaces are cool, even though their inner cores are unimaginably hot. They are nearing the ends of their lives, even though those lives are still measured in millions of years rather than billions. It is gentle to know that such things exist, that somewhere out in the dark, far beyond the familiar stars we name, there are suns so large that planets would be lost inside them. They are not meant for human visiting. They are not meant for human comparison. They are simply there, slowly losing themselves to the space around them, glowing red and vast, finishing their long, brief lives. From the largest, let us move now to the smallest, to the stars that almost were. When a cloud of gas collapses to form a sun, there is a soft and ancient threshold that decides whether or not true fusion will ever begin. A body must be massive enough, dense enough, hot enough at its core, before the patient quantum rules allow hydrogen nuclei to merge in earnest. Below that threshold, the body never quite ignites. It glows for a time, because of the heat of its slow gathering, but it cannot sustain real stellar fusion. It cannot become a true star. These almost stars are called brown dwarfs. They are warm but not bright. They have masses larger than the giant planet Jupiter, often many times larger, but smaller than the smallest red dwarf. They drift through space in the long quiet between true stars and true planets. They are sometimes described as failed stars, although the word failed is unkind. They did not fail. They simply did not have quite enough to begin. They are warm whispers of what might have been. A brown dwarf can fuse a few small amounts of certain heavier forms of hydrogen for a short while, but it cannot keep this up. Over time, it cools, its surface dims. Its light shifts from a deep red into the infrared, into wavelengths that the human eye cannot see. The oldest brown dwarfs are nearly invisible. They float through the galaxy as soft, warm shapes, often unnoticed, sometimes only discovered because of the faint glow of their heat against the cold of space. How many brown dwarfs are out there is still a matter of gentle uncertainty. There may be billions of them in our galaxy alone. There may be more brown dwarfs than there are true stars. Some of them may be wandering between the stars without belonging to any system. Some may be quietly orbiting a more famous companion, almost hidden in its glare. They are the soft cousins of the stellar family, and they remind us that not every gathering of gas becomes a sun. Some gatherings simply become warm, dim shapes, drifting through the dark, holding the memory of what almost was. Now let us pause for a moment and feel the variety we have walked through. There are the patient red dwarfs, small and amber, who will outlive nearly everything. There are the yellow suns like our own, comfortable and steady, generous with their time. There are the white stars, hotter and faster. There are the blue giants, blazing through their main sequence in only a few million years. There are the binary and multiple systems, the long, quiet dances of paired suns. There are the variable stars, breathing in steady rhythms, helping us measure the universe. There are the hypergiants, vast and unstable, soft red giants of unimaginable size. And there are the brown dwarfs, warm whispers in the dark, almost stars and almost not. All of them share the same night sky. All of them are pulled along by the same slow turning of the galaxy. All of them are made of the same simple elements, hydrogen, helium, and traces of heavier matter forged in earlier generations of stars. And yet, no two of them are exactly alike. When you next look up at the stars, try to imagine them as members of a wide, gentle family. The brightest points you see are not necessarily the closest. They may be vast blue giants thousands of light years away, blazing through their brief lives. The faintest points may be small, calm suns much nearer to us, simply quiet about their light. The familiar warm star at the heart of our daytime sky is a yellow medium sun, one of many such stars scattered across the galaxy, no more remarkable than its cousins, except for the small detail of being ours. And invisible to your eyes, woven into the dark spaces between the points of light, there are the others, the patient red dwarfs whispering across trillions of years. The pairs and triples and small families of stars, the breathing variables, the hypergiants slowly losing their outer layers, the brown dwarfs drifting warm and unseen. The night sky you see with your eyes is only a small bright surface above a much deeper world, where countless kinds of stars live their countless kinds of lives. There is no single way to be a sun. There is no one shape that light is forced to take. The universe seems endlessly willing to make stars of many different sizes, temperatures, brightnesses, and rhythms. It is willing to make them in pairs and in trios. It is willing to make them small and patient, or large and brief. It is willing to almost make them in the soft form of brown dwarfs. The garden is wide. The garden is varied. The garden is generous in its kinds of light. Let yourself rest with this for a moment. The sky above you, whether you can see it from where you are or not, is full of these different lives. Some of them are very old. Some of them are very young. Some of them will outlast almost everything. Some of them will be gone in what is, for the universe, only a brief flicker. But all of them are quietly there, breathing in their own ways, shining or almost shining, living through the same vast slow time that holds you in this moment. The next time you look up at the stars, remember that no two are alike. Remember that what looks like a uniform field of small lights is actually a long, quiet gathering of beings, each with its own size, its own color, its own life. And remember that you here, beneath blankets in your own quiet night, are watched over by a sun that is only one of these many kinds. A yellow, steady star, generous with its time, content to shine without drama, content to be ordinary in the most beautiful possible way. The garden of stars is wider than any one mind can hold. We have walked only a few of its paths tonight. There are more we will not visit. There are even stranger residents we will only mention in passing in the parts to come. But for now, let the garden be enough. Let the variety be enough. Let it settle into you like a soft truth you do not need to memorize. The sky is full. The sky is varied. The sky is kind in its many kinds of light. And somewhere among all those many kinds, a yellow, ordinary star is keeping watch over the world that holds you tonight. That is its small, steady gift. The rest of the garden simply keeps on growing in its own time, in its own dark, in its own quiet ways. Every long, quiet life eventually begins to change. The sun has been burning steadily for 4.5 billion years, balancing gravity and fusion in its calm, patient way. But even this balance is not permanent. Deep inside the core of any sun-like star, a slow shift is always taking place. Hydrogen is being turned into helium. Bit by bit, atom by atom, the fuel at the heart of the star is being used up. For most of the star's life, this process is so gradual that it makes almost no difference. The star looks the same, the star feels the same, but somewhere far below its surface, the inventory of hydrogen at the core is slowly drawing down. After billions of years, that inventory begins to thin. The center of the star, which has been quietly running on hydrogen for most of its existence, begins to run low. There is still plenty of hydrogen in the outer layers, vast reserves of it still untouched. But in the core, where the temperature and pressure are high enough for fusion to happen in earnest, the supply is reaching its end. It is a small shift, a quiet shift, but it sets off enormous transformations. When the hydrogen at the very center of the core is mostly used up, fusion there slows. The star's careful balance begins to tip. Gravity, which has been patiently pulling inward this whole time, now has slightly less pressure pushing back against it. The core begins to contract. As it contracts, it grows hotter. And as it grows hotter, something interesting happens in a shell of gas just above the core, where hydrogen still remains. That shell becomes hot enough to begin fusing on its own. Hydrogen fusion has not stopped. It has simply moved outward. The star now has a small inactive core of helium, surrounded by a thin shell where hydrogen fusion is happening more fiercely than before. This new shell of fusion releases more energy than the old core ever did. The star, in its old age, begins to shine more brightly than it ever shone in its youth, and the extra energy pushes outward against the star's outer layers, and they begin to swell. This is the start of a long, beautiful change. The star is becoming a red giant. A red giant is not simply a larger sun. It is a sun whose entire outer self has been gently inflated outward, far beyond its original size. As the outer layers spread out, they cool. Hot plasma that once glowed yellow-white now stretches into thinner, cooler regions. The surface temperature drops, and as the temperature drops, the color of the light shifts. The yellow softens into orange, the orange into red, The vast new outer surface glows in a deep amber light, the color of a quiet evening sky after the sun has set. A typical red giant can swell to 100 times the size of its original star, or more. The largest of them can grow to many hundreds of times their original size. Imagine the sun as it is now, that familiar bright disk in the daytime sky. Now imagine that same sun grown so large that its outer surface stretches outward through the empty space where the planet Mercury currently orbits. Then, further still, past Venus, and, in many cases, further still, all the way out to the orbit of Earth itself. This is what will happen to our own sun in time. It is gentle to say it slowly. In about 5 billion years, our sun will reach this stage. It will not happen all at once. It will not happen in a single dramatic moment. It will happen across hundreds of millions of years, a slow and patient unfolding. The sun will grow gradually larger, gradually redder, gradually brighter and more powerful. The inner planets will feel the change long before the sun reaches its full expansion. Mercury will eventually be swallowed by the growing outer layers, Venus will follow, and eventually, the Earth will find itself in a very different place. The Earth's exact fate during this expansion is still being studied. Some calculations suggest that the swelling sun will reach the Earth's current orbit and engulf it. Other calculations suggest that the sun's mass loss will allow the Earth to drift outward slightly, perhaps escaping the worst of the heat. But all of these possibilities are about a planet that, by then, will be very different from the one we know. The oceans will have boiled away long before the sun reaches its full red giant size. The atmosphere will have thinned. The surface will have grown unrecognizable. This is not a fact to fear. It is simply a fact to notice. It is part of the natural arc of stellar life. Every sun-like star eventually does this. Every sun-like star eventually swells, cools at its outer surface, and reshapes the worlds that orbit it. The Earth has had an extraordinary stretch of calm under the steady light of a young to middle-aged Sunday. That stretch has lasted billions of years. It still has billions to go, and when at last it ends, it will end as part of the same long, gentle story that gave the Earth its beginning in the first place. Try to feel this without alarm. 5 billion years is a length of time that does not really fit inside a human mind. 5 billion years ago, the Earth was not yet here. The first single-celled life would not appear for another 500 million years or more. 5 billion years from now is just as far in the other direction. By then, almost everything that has ever lived on Earth will be deep history. Whatever is here at that point, if anything is, will be as distant from us as we are from the earliest forms of life. The sun's transformation is part of a story longer than any of us, longer even than the entire family of life on Earth so far. So let the red giant phase be what it is. A long, slow change, a patient transformation, a swelling outward of a star that has lived a calm and generous life. As the red giant grows, something else is happening deep inside it. The helium core, which began as small and inactive, is being slowly compressed by the weight of the star above it. It grows denser and denser. It grows hotter and hotter. There is no fusion at its very center yet. The helium is simply being squeezed. But helium, when squeezed and heated enough, has its own kind of fusion it can perform. It can fuse into carbon. It can fuse into oxygen. It only needs the right conditions to begin. In a sun-like star, the conditions arrive somewhat suddenly. In a moment, astronomers call the helium flash. The compressed core finally reaches the threshold where helium fusion can begin, and once it starts, it spreads quickly through the dense core in a short burst of new energy. For the star itself, this is a profound internal event, although it is hidden far inside, behind the vast outer layers. The surface of the red giant does not suddenly flare. The change is quieter from the outside, But the star has now begun a new chapter. It is fusing helium at its core and hydrogen in a shell around that core. For a while, the star settles into another period of relative balance, smaller and slightly less luminous than its peak as a red giant, but still much larger and brighter than it was in its main sequence days. This new balance is shorter than the old one. The original main sequence lasted billions of years. This helium fusing stage will last only about 100 million years. Long by any human standard, but only a small fraction of what came before. During this stage, the star's core is gently producing carbon and oxygen. These are the elements that will become so important to everything that comes later. The carbon in every plant, the carbon in every body, the oxygen in every ocean, the oxygen in every breath, all of it being forged, atom by atom, inside the calm helium-burning cores of aging stars. The universe is, in this quiet way, slowly building the matter that life will eventually use. But the helium too begins to run out. The core grows full of carbon and oxygen, and the helium there begins to thin. The fusion at the center slows. Once again, the balance tips. And once again, the star begins to change. For a star of our sun's mass, the changes now become more complicated. The core contracts again, the temperatures climb. Helium fusion moves outward into a new shell. The star begins to swell even larger than before. Its outer layers grow even cooler, even redder, even more loosely bound to the rest of the star. The red giant becomes something even softer at its edges. Astronomers sometimes call this the asymptotic giant phase. But you do not need the name. You only need to know that the star, having burned through helium at its center, is now living through a brief and beautiful instability. In this late stage, the star can pulse. It can swell and contract on slow rhythms. Its outer layers become so far from the core that gravity holds them only loosely. The fusion shells inside the star can become uneven, sometimes flaring slightly in soft pulses called thermal pulses. With each pulse, more of the outer atmosphere drifts outward into space. A red giant in this stage is gently losing itself. Its outer layers are being slowly released, carried away on soft stellar winds. The star is shedding its skin into the dark. This is not violent. It is more like a long exhale. Material that once belonged to the star now begins to drift outward, layer by layer, ring by ring, into the surrounding space. You may find it lovely to know that this material is the very stuff future stars and planets will be made from. The outer layers of a dying sun-like star are rich in carbon and other elements that did not exist in the early universe. When this material drifts outward, it joins the slow, cold clouds between the stars, ready to be gathered again, ready to become part of a new nursery one day. The dying of a star is, in this sense, also a kind of giving. As the red giant continues to pulse and shed its outer layers, the star eventually reaches a point where it cannot quite hold on to those layers any longer. The outermost gas drifts away in great wide shells. The exposed inner regions of the star, much hotter than the cool outer surface, begin to send out energetic light. That light catches the drifting shells of gas and makes them glow. What you see when this happens is one of the most quietly beautiful sights in the universe. A soft glowing shape, sometimes a perfect ring, sometimes a delicate butterfly, sometimes a layered nest of curving shells, hanging in the dark around a small, bright central point. Astronomers, long ago, gave these objects the name planetary nebulae. The name is misleading. They have nothing to do with planets. It is just that, when they were first seen through small telescopes, they looked like soft round disks, reminiscent of planets. But there are no worlds inside them. They are the gently glowing exhalations of dying stars. There is one planetary nebula in the small constellation Lyra called the Ring Nebula. It looks almost exactly as its name suggests. A pale glowing ring, surrounded by a softer outer halo, with a small bright dot in its very center. That central dot is what remains of the star that made the ring. The ring itself is the star's slowly expanding atmosphere, blown outward in thin shells over thousands of years. Each shell is light years across. Each shell is illuminated by the small hot remnant at its heart. There is another, even more elaborate, called the Cat's Eye Nebula. It lies in the constellation Draco. When the Hubble Space Telescope photographed it, the image revealed an intricate structure of concentric shells, jets, and braided strands of glowing gas. It looks almost like a great cosmic flower, slowly opening in the dark. Each layer corresponds to a different episode of mass loss from the dying star at its center. Each layer is a chapter in that star's long unraveling. There are many such nebulae. The Helix Nebula, which looks almost like a great cosmic eye. The Eskimo Nebula, with its rounded shells. The Butterfly Nebula, and the Ant Nebula, with their delicate bipolar shapes. Each one is unique. Each one is the soft signature of a star that has reached the end of its red giant life and is offering its outer layers back to the galaxy. Planetary nebulae do not last very long by cosmic standards. The shells of gas expand outward at speeds of tens of kilometers per second, and over a few tens of thousands of years they thin and fade until they are no longer easily visible. A planetary nebula is a brief and gentle work of cosmic art, lit by the soft last glow of its star, before drifting outward into the wider dark and becoming part of the slow material between the stars. For a moment, picture one of these nebulae as it is. A pale glowing ring, or butterfly, or layered shell, hanging in the dark, with a small bright remnant at its center, surrounded by silence. Picture the slow expansion of the gas, almost too slow to see, drifting outward into space. Picture how, after thousands of years, the gas will be so thin and so far apart that it will simply become part of the wider quiet between the stars. The star's outer self will no longer be a clear shape. It will be a gentle enrichment of the cold dark. And at the very center, the small, bright remnant remains. This remnant is the next stage of the star's life. After the red giant phase, after the planetary nebula, what is left behind is a small, dense object that no longer fuses anything at all. It is the carbon and oxygen core of the old star, exposed to space, no longer surrounded by the outer layers that once hid it. This is the white dwarf. A white dwarf is a strange and gentle thing. It is roughly the size of the Earth, sometimes slightly smaller, sometimes slightly larger. But it carries about half the mass of the original star, packed into that small space. A spoonful of white dwarf material would weigh many tons. Its density is almost incomprehensible by any everyday measure. It is the calm, dense ember of what once was a sun. When the white dwarf first appears, it is extremely hot. Its surface temperature can be more than 100,000 degrees. It shines with a fierce white-blue light, but it has no fuel of its own anymore. There is no fusion at its core. There is nothing pushing outward to keep it hot. It is simply a small, dense object glowing with the leftover heat of all those billions of years of stellar life. And so it begins to cool. It cools slowly, very slowly. White dwarfs are excellent at holding on to their heat. They radiate it outward only over long stretches of time. A young white dwarf, fresh from the planetary nebula stage, may take billions of years just to cool from its initial brilliance to a softer, warmer glow. It will take many billions more to become only faintly visible. And it will take longer still, perhaps far longer than the current age of the universe, to cool completely. In fact, the universe is not yet old enough for any white dwarf to have fully cooled to the lowest possible temperature. The very first white dwarfs ever formed in our galaxy, those born from the first generation of sun-like stars, are still warmer than the surrounding space. They are still glowing softly. They are still radiating away the last warmth of stars that lived and changed long before the Earth ever existed. In the unimaginable far future, when whatever comes will come, those white dwarfs may finally cool to a deep cold and become what astronomers sometimes call black dwarfs. Dark, dense embers, no longer glowing. Quiet, small objects drifting through whatever the galaxy will be at that point. But that is a very long time from now. For all practical purposes, white dwarfs are eternal. They will spend the rest of forever slowly giving up their heat to the dark. There is a small, comforting thought in this. After all the gathering, after all the long main sequence, after the red giant phase and the planetary nebula and the soft drifting of outer layers, what remains of a sun-like star is a small, calm presence. A dense ember the size of a planet, no longer fusing, no longer changing in any sudden way, just slowly, patiently, releasing its old warmth into the night. The sun, in its time, will become one of these. After it has finished its red giant phase, after it has gently shed its outer layers as a soft planetary nebula, what will remain of our own sun will be a small white dwarf, about the size of the Earth, surrounded by whatever is left of its planetary system. The outer planets may still be there, orbiting at greater distances. The inner planets may be gone, or may have drifted outward, or may be small reshaped remnants of their former selves. The white dwarf at the center will not give much warmth. It will glow softly. It will hold its long heat for billions of years more, slowly releasing it into the dark. It is strange to think of the sun that way. The same sun that warms your skin today, the same sun that lit every morning of your life. One day, in a very long time, it will be a small, dense ember, quietly cooling. The light it gave will have long since reached the planets, and reached the further stars, and reached the soft, empty regions between galaxies, and traveled on. The sun's life will have changed forms. It will still be there, in a sense, but it will be a quieter version of itself. Try not to feel sad about this. The story is not one of loss, it is one of transformation. Stars do not disappear when they reach this stage. They become something else. They become small, dense lamps that hold their warmth for nearly forever. They leave behind soft, glowing shells of gas that drift outward and become part of the next generation. They contribute the carbon and oxygen they made in their hearts to the wider universe. The dying of a sun-like star is, in many ways, a long, slow gift, and the gift is shared. Every white dwarf in the galaxy, and there are billions of them already, is a small, calm reminder of a star that once lived a full life. Every planetary nebula, while it still glows, is a soft work of cosmic art lit by one of these embers. The galaxy is quietly full of these things. They are not loud. They are not obvious to the unaided eye. But they are there, scattered through the dark, slowly cooling, slowly fading, the long, quiet endings of long, quiet lives. Pause for a moment with this. Picture the sun, billions of years from now, as a small white dwarf. Picture the planetary nebula it once threw off, long since drifted away and lost into the wider gas of the galaxy. Picture the outer planets still slowly turning around the small dense ember, in orbits that no longer feel any warmth. Picture the universe much older than it is now, full of these quiet remains. There is a peacefulness in the image. Nothing is rushed. Nothing is angry. The star simply did what stars do. It gathered, it shone, it grew, it released its outer self, and it settled into a long, calm afterlife as a small, cooling lamp. Not every star ends this way. There are larger stars whose endings are very different, whose lives close with sudden brilliance rather than slow release. We will follow those endings in the next chapter of our night together. They are spectacular in their own way, and they leave behind even stranger remnants. But for now, let us stay with the soft endings. Let us stay with the sun like stars, with the gentle transformations, with the red giants and the planetary nebulae, and the patient white dwarfs. This is the long unraveling, slow, beautiful, inevitable, part of the same patient story that began with cold clouds and quiet ignitions. Every sun that has ever calmly lived eventually changes in this way. Every sun, every quiet, calm star, including, in time, our own. So let your breath grow longer here. Let your body settle a little deeper. The universe knows how to age its stars. It does not rush them. It does not waste them. It allows them to swell, to glow, to release, and to rest. It allows them to become small, calm embers in the dark, slowly cooling, slowly fading, holding their old warmth for what feels like forever. The sun is doing its work. It is in its long, calm middle. Far ahead of it, the slow unraveling waits patiently, as it has waited for every sun before. Far ahead of you, the night ahead waits patiently too. And right now, in this moment, everything is steady. Everything is held. The stars are turning quietly. The sun is keeping its old promise, and you can rest. Not every star fades gently. Some stars are simply too large to slip away as a soft red giant. Some stars carry too much mass, too much gravity, too much fire at their cores to follow the patient road of the Sunday. Their endings come more brightly, more suddenly, and they leave behind some of the strangest remnants in the universe. But even these endings, dramatic as they are, belong to the same slow and ancient rhythm. They are not violence for its own sake. They are simply what happens when a very large star reaches the end of what it can do. To understand these endings, we need to slow down and look inside a massive star while it is still alive. A massive star is one that begins life with many times the mass of our Sunday, perhaps 8 times, perhaps 20, sometimes 50 or more. Within these great suns, the cores are far hotter and far denser than anything inside our own. The pressure is staggering. The temperature climbs into the hundreds of millions of degrees, and at the very last stages, into the billions. These are conditions our sun will never reach. The sun's core simply does not have enough weight pressing down on it to push the temperature that high. But a massive star, with all its extra mass piled inward, can push its core into states our sun will never know. These extreme conditions allow a massive star to fuse not only hydrogen and helium, but heavier elements too, and they allow it to do so in a beautifully layered way. Picture, very gently, the inside of one of these great suns near the end of its life. At the very core, the temperature is so high that elements deep in the periodic table can fuse. Around the core, in a soft shell, lighter elements are fusing. Around that shell, in another shell, even lighter elements are fusing, and so on outward, layer after layer, each layer cooler than the one beneath it. The structure inside the star comes to resemble the rings of a great tree. Each ring is fusing a different kind of fuel. Each ring corresponds to a different stage of the star's long story. In the outermost layers, hydrogen is still being fused into helium, the same simple reaction that powers our own Sunday. Beneath that, helium is being fused into carbon. Beneath that, carbon is being fused into oxygen and neon. Beneath that, oxygen is being fused into silicon, and at the very center, silicon is being fused into iron. Each new layer takes less time than the last. Hydrogen burning in such a star may last for millions of years. Helium burning may last for 100,000. Carbon burning, perhaps a few hundred years. Oxygen burning, only a few months. And silicon burning, the very last stage, may last only a single day. A day. After millions of years of patient life, the star's final layer is created in a final 24 hours of quiet inner work. It is gentle to imagine. A great star, calmly going about its long existence, slowly building up these layers inside itself: carbon, oxygen, neon, silicon, iron, each one forged in its own ring, each one a small contribution to the chemistry of the universe. By the end of its life, the star is carrying within itself a record of everything it has done. But there is a problem with iron. Iron is special. Every fusion reaction that came before it released energy. When hydrogen fused into helium, a small amount of energy came out. When helium fused into carbon, more energy came out. Each step, all the way up to silicon, released some energy that helps support the star against gravity. But iron is different. Fusing iron does not release energy, it absorbs it. To fuse two iron nuclei into something heavier, you must pour energy into the reaction. The star can no longer support itself by making more iron. So once iron begins to gather at the very center of a massive star, the long balance that has held it together starts to fail. The iron core grows heavier and heavier. The temperature climbs higher and higher. But no new fusion energy comes from this core. There is nothing to push outward against gravity. The pressure that once held the star up is fading, even as gravity continues to pull inward. This is the quiet edge of the moment. The star, after millions of years, has reached a point where it can no longer hold itself up. What happens next happens very quickly. In a fraction of a second, the iron core, no longer supported, simply gives way. It collapses inward under its own immense weight. The collapse is breathtaking in its speed. The core, which is already smaller than the Earth, falls in on itself in less than a heartbeat. The outer layers of the star, which until that moment were resting on the support of the core, suddenly have nothing beneath them. They begin to fall inward as well. But the falling material does not simply vanish. As the core collapses, it crushes itself into a state of unimaginable density. The atoms are pressed so close together that even their electrons are forced into the protons, creating neutrons. The whole core becomes, in that instant, almost entirely made of neutrons, packed so tightly that the entire core, which may have once been the size of a small planet, is now compressed into a sphere only a few tens of kilometers across. At that density, the collapse cannot continue further. The neutrons resist being pressed any closer. The inward fall hits a wall, and the core suddenly stops. A shock wave, born from this sudden stopping, races outward through the rest of the falling star. Combined with a vast flood of tiny particles called neutrinos, which carry away most of the energy of the collapse, the shock wave reverses the fall of the outer layers. Material that was rushing inward is suddenly thrown back outward. The outer layers of the star are launched into space. This is the supernova. It is a vast release of light. The whole outer body of the star is blown outward at thousands of kilometers per second, glowing with an intensity that is difficult to imagine. For a few weeks, a single supernova can outshine the entire galaxy in which it occurs. A single dying star, briefly more luminous than the combined light of 100 billion others. But please do not feel alarmed by this. It is light, more than anything. It is not a fire that will reach you. It is not a sound that will wake you. It is a slow flowering of brilliance, far away, in places so distant that even the closest supernovae from history were soft to the human eye. The word violence does not quite fit. The reality is more like a vast, deep blooming, a star at the end of its life giving back, all at once, the energy and material it had been holding for millions of years. Across human history, a few supernovae have appeared in our skies bright enough to be noticed. They were rare. They were small, soft mysteries, recorded by careful watchers who did not yet know what they were seeing. One of the most famous occurred in the year 1054. People in China, Japan, and parts of the Arab world looked up and noticed a new star in the sky. It was bright enough to be seen in daylight for several weeks, bright enough to remain visible at night for nearly 2 years. Chinese astronomers wrote it down in their court records, describing where it appeared and how slowly it faded. Other observers in different parts of the world wrote of it too. They did not know what it was. They simply noted that, for a while, something new had been added to the sky. We now know that what they were seeing was a star at the moment of its death, thousands of light years away. The light from its supernova had been traveling through space for many centuries before it reached the Earth in that particular year. The people who watched it had no way of knowing how old its light was. They only knew it was there, soft and quiet, hanging in the sky for a season before slowly fading away. That supernova is known today as SN 1054. And although the bright new star eventually faded from view, what it left behind is still visible to us, in a soft and beautiful form. The supernova blew outward, a vast shell of gas, and that shell is still expanding into space today, glowing in delicate threads of color. It is called the Crab Nebula. If you look at images of the Crab Nebula taken by modern telescopes, you can see the gentle aftermath of that long-ago death. Long filaments of glowing gas, like fine fibers of a great cosmic flower, drifting outward at thousands of kilometers per second. They have been drifting for nearly 1,000 years now, ever since the light first reached Earth. The shell is still growing. It is still being lit by the remnant at its heart. The Crab Nebula is, in a quiet sense, the same supernova that those watchers in 1054 wrote about. It is just much more slowly visible now. Another famous supernova lit the skies of the year 1572. The astronomer Tycho Brahe in Denmark noticed a new star in the constellation Cassiopeia, almost as bright as Venus. He watched it for months, recording its brightness with great care. He wrote a small book about it, with a title that simply meant a new star. At the time, the prevailing view of the heavens held that the realm of the stars was eternal and unchanging. Tycho's careful observations helped show, gently and clearly, that the heavens were not unchanging at all. New stars could appear, and old ones could fade. The universe was a place of slow change, even at the level of the distant lights. Tycho's new star, like SN 1054, eventually faded from view. We now know that it too was a supernova, the death of a star many thousands of light years away. The shell of gas it threw off is still expanding into space, and modern telescopes can see it in faint colored loops, the soft remnant of a death that arrived in our skies more than 4 centuries ago. A few decades after Tycho, another bright new star appeared. The astronomer Johannes Kepler observed it in 1604, and his name has been attached to it ever since. Kepler's supernova was the last one observed within our own galaxy that became bright enough to be easily seen by the unaided eye. Since then, no nearby star in the Milky Way has ended its life close enough and bright enough for us to see clearly in our own skies. The galaxy has been quiet, in that sense, for hundreds of years. But supernovae are happening, all the time, in other galaxies. With modern telescopes, astronomers see dozens of them every year, scattered across the wider universe. Each one is the death of a single massive star, far away, in a galaxy that may itself be millions or billions of light years from us. Each one, by the time it reaches us, has spent that long traveling. We see its brief brilliance long after the star itself has gone. We see only the light it sent out as it died, finally arriving, after its long, quiet journey across the dark. There is something tender in this. A supernova is the brightest single event in the lifetime of a star, brighter than anything else the star will ever do. And yet, by the time we see it, the star itself is gone. The light is the last gift. The light is what remains in motion. Across the universe, this last brightness is endlessly traveling. New supernova light is reaching the Earth every day, from older deaths in distant galaxies, soft signals across the deep. But the supernova is not the end of the story. Even at the heart of this great release, something remains. When the outer layers of a massive star are blown outward as a supernova, the inner core does not always disappear. In many cases, the small, dense core that began the collapse is left behind. What it becomes depends on how much mass remained. If the leftover core has a mass roughly between 1 and 2 times that of the Sun, it stays in its compressed state of pure neutrons. This is the neutron star. A neutron star is one of the strangest things in the universe. It is small, so small. A neutron star is typically only about 20 kilometers across. You could place one across a small city and it would fit. And yet it carries within it more mass than our entire Sunday. A teaspoon of neutron star material would weigh hundreds of millions of tons here on Earth. It is matter compressed to the very edge of what compression allows. The surface of a neutron star is extreme by any measure. Its gravity is so strong that an object dropped from above would strike the surface at a fraction of the speed of light. Its magnetic field is so intense that no instrument here on Earth comes close. Its temperature, when it first forms, is around 1 trillion degrees, though it cools quickly to much lower numbers. And yet, somehow, neutron stars are still small, calm presences in the wider universe. They sit in their tiny, dense states, sometimes for billions of years, slowly spinning, slowly radiating away their leftover heat. They are the patient bones of stars that have given the rest of themselves away. Many neutron stars spin very rapidly. When a massive star's core collapses, it carries within it whatever rotation the star had before the collapse, but compressed into a much smaller object. Just as a spinning skater pulls in their arms to spin faster, a collapsing core spins faster as it shrinks. Some young neutron stars rotate hundreds of times per second. When a spinning neutron star has a strong magnetic field, and when its magnetic axis is tilted relative to its rotation axis, something quietly remarkable happens. The neutron star emits beams of radio waves along its magnetic poles. As the star rotates, those beams sweep across the sky like the beam of a great cosmic lighthouse. If the Earth happens to lie in the path of one of those beams, we receive a small, soft pulse of radio waves with each rotation. These spinning neutron stars are called pulsars. The first pulsar was discovered in 1967 by Jocelyn Bell Burnell and her colleagues. They detected a regular series of radio pulses arriving from a single point in the sky with such precise timing that at first they wondered if it could be a signal from some other intelligence. After more careful study, they realized they had found something different and equally astonishing. A small neutron star spinning many times per second, sending its quiet radio pulses across the dark. Today we know of thousands of pulsars in our galaxy. Some pulse a few times every second. Some pulse hundreds of times every second. Some are old and have slowed down to lazier rhythms. But all of them are, in a sense, the singing of dead stars. Tiny, dense remnants of supernovae, still spinning, still emitting, still tracing soft signals across the universe, long after the dramatic light of their birth supernova has faded. The Crab Nebula has one of these at its heart. At the center of those delicate filaments of gas, left over from SN 1054, sits a pulsar that rotates about 30 times every second. It pulses across the radio bands, across the visible light, even across the high-energy X-rays. The same star whose death lit up the skies of ancient watchers in 1054 is still there, in a sense. It is just much smaller now. It is a small, dense, city-sized object, turning rapidly, singing softly into space, surrounded by the slowly drifting flowers of its own outer body. There is something tender in that image. A star whose visible brightness has long since faded is still alive in this changed form, still spinning, still saying something, still here. But not all massive stars leave neutron stars behind. Some are too large even for that. If the leftover core of a supernova has too much mass, perhaps more than 2 or 3 times the mass of the Sun, then even the neutrons cannot resist gravity any longer. The collapse continues past the neutron star stage. It continues until the core has compressed itself into a region so small and so dense that not even light can escape from it. The star has become a black hole. A black hole is often spoken of in dramatic terms, as a monster, as a destroyer, but that language fits poorly. A black hole, especially the kind formed from a single dying star, is not a hungry beast roaming through space. It is simply a region where the gravity is so strong that the usual ideas of inside and outside no longer behave the way they do anywhere else. Space itself folds inward toward the center. Time slows near the surface. The light that tries to leave is bent back into the dark. From a great distance, a stellar mass black hole, the kind formed from a single star, is small, perhaps only 10 or 20 kilometers across in the region from which nothing returns. Around it, the gravity is strong, but not infinitely far-reaching. If our Sun were somehow replaced by a black hole of the same mass, the Earth's orbit would not change. The Earth would still travel around it as it does now. There would be no light, no warmth, no day or night in the usual sense. But the planets would not be pulled inward. They would simply continue in their familiar paths around an unseen center. A stellar mass black hole is, in some ways, just another stellar remnant. Like a white dwarf, it is what remains when a star has finished its life. Like a neutron star, it is dense, far denser, but still a small object compared to the wide reach of space. It is the natural ending of the largest kinds of stars. It is not a wrong note in the symphony. It is the quiet last chord of the very largest movements. Sometimes a black hole forms quietly, without the spectacle of a supernova. The star simply collapses inward, and the outer layers fall into the new black hole instead of being thrown outward. From the outside, the star may seem to simply disappear from the sky. There are a few suspected cases of this kind of soft collapse in nearby galaxies, where a previously visible bright star quietly vanished without leaving the usual fireworks. The largest stars seem to be allowed, in some cases, to choose this gentler form of ending. And then there are the supermassive black holes, the kind that sit at the centers of galaxies, including the heart of our own Milky Way. These are not formed from a single star. They grow over very long times, from many smaller mergers and slow gathering of matter. They are different from the stellar mass black holes we are speaking of tonight. We will leave them gently aside for another night. What we want to feel tonight is that even the most spectacular ending of a star is part of the same slow and ancient rhythm. The largest stars cannot fade gently as red giants. Their endings come in supernovae, in flashes of light bright enough to outshine entire galaxies for a few weeks. They leave behind neutron stars that spin and sing in radio waves. They leave behind black holes that sit quietly, folding space inward, no longer fully part of the visible cosmos. They scatter heavy elements into the space around them, the iron and silver and gold and many other heavy atoms, gifts to the next generations of stars and planets. Everything heavier than iron, in fact, was forged in or near these endings. The gold in any ring you have ever seen, the silver in any old coin, the iodine in any thyroid gland, the calcium in any bone, all of it ultimately came from stars that died long before our sun was born. Sun-like stars give back carbon and oxygen and other lighter elements. Massive stars give back the heavy elements in the patient layers built up over their lives and in the explosive moment of their supernovae. And neutron star mergers, when two neutron stars eventually spiral into each other in some binary systems, are now understood to add even more heavy elements to the mix. Every kind of stellar death contributes something. The galaxy is gently enriched, generation after generation. Each new cloud of gas that gathers to form new stars is just a little richer in heavy elements than the one before. Our own sun, when it formed, was not made from pristine hydrogen and helium. It was made from material already enriched by countless earlier deaths. The Earth itself, every atom of it, heavier than helium, came from somewhere, from some earlier star, from some earlier ending, from some great patient gift that was given before our planet existed. So even the spectacular endings are soft in this way. They are bright, they are sudden, they light up entire galaxies for a few weeks. They leave behind objects so strange that they almost feel like myths. And yet, they are simply the way the largest stars do their part. They are the way the universe recycles its largest gifts. They are the way the heavy elements of life are made and shared. When you next imagine a supernova, try to think of it not as a sudden violence, but as a slow gift arriving with great brightness. The star spent millions of years quietly building up the materials it would one day release. The release itself is brief, but what it scatters into the surrounding space will become part of clouds, that will become part of new stars, that will become part of new worlds, and maybe, in time, part of new life. Perhaps, far in the future, in some other galaxy, on some other small blue planet, someone will look up at a night sky lit by stars whose atoms once passed through the great release of a supernova that happened tonight, somewhere in some distant corner of the universe. These endings are not the end of anything. They are passages. They are transformations on a larger scale than the gentle fading of a sun-like star, but they are transformations all the same. They belong to the same rhythm, the same slow story, the same patient turning of the cosmos. Rest with that thought. Even the largest stars, even the most dramatic deaths, are held in the same gentle hands that hold our own quiet Sunday. The universe has room for soft endings and bright endings, for white dwarfs and neutron stars, for planetary nebulae and supernovae, and the quiet folding of space into black holes. All of them belong. All of them are part of the work. And somewhere, even now, a massive star is reaching the last day of its silicon burning. Somewhere, a core is just beginning to fall. Somewhere, a brief brilliance is preparing itself, a great gift of light and matter that will not reach us for a long time, but is on its way through the dark. We do not need to watch for it. We do not need to wait. The universe has been making and unmaking stars in this way for more than 13 billion years, and it is making and unmaking them still. Breathe out gently. Let the brightness be far away. Let the endings be soft, even when they are not. The largest stars, like the smallest, are doing exactly what their nature allows. They are giving back what they were given. They are turning what they once gathered into something new. And the universe, which makes room for all of it, keeps turning quietly, holding even the most spectacular departures inside its long, patient night. When a star releases its outer layers, whether softly as a planetary nebula or brightly as a supernova, the material does not simply disappear. It drifts outward into the space between the stars. It joins the wider gas that fills the gaps of the galaxy. It mixes, slowly, with the older material that has been there for ages, and in time, it becomes part of something new. This is the quiet truth at the heart of stellar life. Nothing is wasted. The matter blown outward by dying stars becomes the raw material for new ones. The atoms that once burned in the heart of an ancient sun do not vanish when that sun changes. They drift, they cool, they wait, sometimes for millions of years, sometimes for hundreds of millions. And eventually, somewhere in the slow turning of the galaxy, they gather again into a new cloud, a new nursery, a new generation of stars. The universe has been doing this for more than 13 billion years. Star after star, generation after generation, the same atoms have been passing through different bodies of light. Hydrogen and helium are the oldest materials present since the very beginning of the cosmos. But the heavier elements, the carbon and oxygen and nitrogen, the silicon and iron, the silver and gold. All of these came from stars. They were forged inside the great patient cores of suns long gone, or in the bright endings of massive stars, or in the slow drifting layers shed by red giants in their old age. Every heavier atom in the universe carries within it a small, quiet history. Each one was, once, inside a star. When a supernova fades, and its shell of gas slowly drifts outward, what it leaves behind is a region of space slightly richer than before. Carbon and oxygen, scattered by red giants and supernovae alike. Iron, born in the very last hours of a massive star's life. Gold and platinum and uranium, forged in the extraordinary conditions of supernovae and neutron star mergers. Each new ending leaves the surrounding gas just a little more complex than it was before. Over long ages, these slow enrichments add up. The galaxy is not the same galaxy it was when it first began making stars. The clouds of gas in the Milky Way today are richer in heavier elements than the clouds of gas were a billion years ago. Those clouds in turn were richer than the clouds a billion years before that. The universe is patiently building up the materials it needs to make worlds and bodies and quiet listeners. Each generation of stars adds something to the inheritance of the next. Our own sun is a child of this long process. It did not form from pristine first material. By the time the sun gathered itself together, around 4.5 billion years ago, the galaxy had already been making stars for nearly 9 billion years. Many generations of suns had lived and died before. Many supernovae had already gone off. Many red giants had already shed their soft outer layers into the dark. By the time our sun's birth cloud began to draw inward, it was already enriched with the carbon and oxygen and iron of earlier deaths. It was already carrying within it the gifts of stars that no longer existed. The Earth carries those gifts too. Every atom of carbon in every leaf, every tree, every bird and every body came originally from some earlier star. Every atom of oxygen in every breath you take was forged in an old sun. Every atom of iron in your blood, every atom of calcium in your bones, every grain of silicon in the stones and sands of the world was made inside a star that no longer shines as it once did. We are quite literally made of stardust, a phrase that has become familiar enough to almost lose its meaning. But the meaning is gentle and true. Pause with this for a moment. The iron in your blood is the same iron that was forged in the last day of some massive star's life, long before the Earth existed. The calcium in your bones came from the cores of red giants, or from the supernovae of even larger stars. The water in your body holds oxygen made inside ancient stellar hearts. The carbon that builds every living thing was once at the heart of some long-gone sun. This is not metaphor. It is simply the chemistry of the universe. The atoms that make you have been on a long journey. They drifted through cold clouds. They were drawn into nurseries. They were heated in stellar cores. They were released in soft red giant winds, or in the bright endings of supernovae. They drifted again. They were gathered again. They became part of the cloud that made the sun and the earth. They became part of the soil, the seas, the air, the bodies of countless living beings. And now they are part of you. Here, in this quiet night, you are not separate from the cosmos you have been hearing about. You are made of it. The same hydrogen that fuses inside the sun is in the water of your body. The same iron that holds neutron stars together is in your blood. The same calcium that drifted from old red giants is in your bones, your teeth, the small shape of your jaw, the curve of your hand resting on the blanket. You are part of the great, long story we have been wandering through tonight. Take that gently. There is no need to feel small about it. There is no need to feel large. It is simply a quiet inheritance. The universe has been making and unmaking stars for 13 billion years, and along the way, it has also made you. Astronomers have a soft way of naming the generations of stars they study. The very first stars, born from the pure hydrogen and helium of the early universe, are sometimes called population 3. They are mostly theoretical, almost too faint and too old to find, but they were the first true sources of heavier elements. The next generation, the old stars still scattered in the outer regions of galaxies, are called population 2. These are some of the oldest stars we can see. They are poor in heavy elements because they formed when the galaxy was still chemically young. They are often found in great globular clusters, tight gatherings of older suns that orbit the centers of galaxies like distant memories. The younger, more enriched stars, including our own sun, are called population 1. These stars formed from clouds that had already been enriched by earlier generations. They contain more heavy elements. They live in the disks of spiral galaxies, in the bright arms where star formation still continues. They are surrounded, more often than not, by planets, because the heavier elements that planets need were already present in the clouds from which they formed. The Sun is a population 1 star. So are most of the stars near us. So are the stars that gave us our local night sky. They are children, in a chemical sense, of countless earlier suns. Their light shines through bodies that contain the gifts of all those past generations. It is gentle to think of the night sky in this way, as a gathering not just of present stars, but of accumulated histories. Each of those points of light carries within it the atoms of stars that came before. Each one is part of a long story. None of them began from nothing. None of them are alone. And the galaxies themselves are great gardens, slowly turning, in which all of this happens. A spiral galaxy like our Milky Way is full of regions where new stars are being born, regions where mature stars are quietly burning, regions where old stars are reaching their endings. The arms of the spiral are bright with young hot stars, lighting up clouds of gas where new nurseries are forming. The disk between the arms is full of calm, middle-aged stars, living their long, patient lives. The center of the galaxy is older, full of stars that formed long ago, slowly turning in great quiet swarms. From a great distance, a galaxy looks still. It looks like a single soft spiral, almost a flower made of light. But on a closer view, it is in constant slow motion. Stars are being born. Stars are aging. Stars are ending. The gas of the galaxy is endlessly cycling between the cold clouds and the hot bodies of suns. The heavy elements made in one generation are passed gently to the next. The galaxy is not a static painting. It is a slow garden, where everything blooms and fades, and blooms again, on timescales that stretch far beyond any one life. Other galaxies do this too. Some of them are spirals like ours. Some of them are great elliptical clouds of older stars, where new star formation has slowed. Some of them are small and irregular, still in the early stages of their own cosmic shape. All of them, in their own ways, are part of the same long pattern. All of them are gardens of light. All of them are slowly turning, slowly aging, slowly mixing the material of their stars. And among all these galaxies, our own is one, a spiral, a quiet wheel of light, turning gently in a small corner of the wider universe. Inside it, on one of its arms, there is a single yellow star. Around that star there is a small blue and green and white world. On that world, in some quiet room, you are lying down, you are listening. You are part of the garden too. Let the picture grow soft now. We have travelled far tonight. We began in the cold clouds, where the first quiet gatherings of gas began to form. We moved through the long, patient lives of stars, the calm, steady years of our own sun and her many cousins. We walked the wide garden of stellar variety, from the patient red dwarfs to the brief blue giants, from the binary pairs to the great hypergiants. from the steady variables to the soft brown dwarfs. We watched the slow unraveling of sun-like stars, the swelling into red giants, the gentle release of planetary nebulae, the long calm afterlife of white dwarfs. And we walked carefully through the spectacular endings of the largest stars, through the layered fusion of their final days, the brief brilliance of their supernovae, the small singing remnants of neutron stars and pulsars, and the quiet folding of space into black holes. All of it belongs to the same story. All of it is part of the same great cycle: birth, life, aging, ending, return, birth again. The universe has been telling this story for more than 13 billion years, and it is telling it still. Somewhere right now, in a cold cloud of gas far from here, a new sun is gathering itself in the dark. Somewhere right now, a calm, middle-aged star is shining steadily over a small blue world. Somewhere right now, an old red giant is shedding its outer layers in a soft, slow exhale. Somewhere right now, a massive star is reaching the last hours of its silicon burning. And somewhere right now, a faint white dwarf is releasing the last of its old warmth into the surrounding space. All of this is happening at once. All of it is held within the same quiet turning of the cosmos. None of it needs your attention. None of it needs your worry. It is simply going on, as it has gone on for ages, and as it will go on long after any of us. Now, let yourself come gently back to your body, to the room around you, to the warmth of the blankets, to the soft surface beneath your head. The galaxy is still turning. The sun is still shining on the other side of the earth. The stars are still in their slow, patient motions overhead. And here, where you are, there is only this quiet moment, only this breath, only this rest. Notice your breathing. There is no need to change it, just notice it. The slow rise and fall, the simple coming and going of air, the same air that has passed through countless lives before yours, the same oxygen that drifted from old stellar deaths, the same atoms that have been moving through the world for a long, long time. Notice your body, the weight of it on the bed, the warmth gathered in the small spaces of you, the places where you are softly held. Let those places relax just a little more. Let your shoulders settle. Let your hands grow heavy. Let your jaw soften. There is nowhere to be tonight. There is nothing more to do. We have walked tonight through cold clouds and patient suns. We have stood at the edges of dying giants and watched soft white dwarfs cool in the dark. We have heard the singing of pulsars and felt the slow folding of space around the quiet remnants of the largest stars. We have followed the long cycle of birth and ending and birth again, the great rhythm that makes the universe go on. And now we come, slowly, to the end of this walk. There is nothing more to add. There is nothing more to know tonight. The stars will keep doing what they have always done. The galaxy will keep turning. The sun will rise tomorrow on this small blue world, and somewhere in its long, calm middle, it will keep its old promise once more. If you would like to walk with me again on another night, this channel will be here. There are other journeys waiting, other gentle subjects, other long, quiet wanderings through the wonders of the universe. Whenever you return, the path will be open. There is no hurry. There is no expectation. Just an open door when you next feel like coming through it. For now, let this be enough. Let the cold clouds be far away. Let the patient suns burn quietly in their own time. Let the great endings happen in their distant corners. Let the long cycle keep turning, without any need for your attention. Notice your breath one more time. Slow, easy, just there. Feel the weight of your body, heavy, held, safe in the dark. Feel the warmth around you, steady, soft. You are made of the same patient atoms that built the stars. You are part of the same long, gentle story, Tonight, you can simply rest inside it. The sun is still keeping watch on the other side of the world. The stars are still turning. The garden is still slowly blooming in its own deep time. You are safe. You are warm. You are held. Let the journey go now. Let your thoughts grow softer. Let your eyes stay closed. Let your breath grow slow. Let the universe carry on without you for a while. It will be here when you wake. The stars will still be there. The sun will still rise. You can rest now. You can drift now. You can let go. Sleep gently. Sleep softly. Sleep well. Good night.